Volume 1, Foundations, Frameworks, and Quantitative Methodologies, written in the appropriate tone and style for an academic and professional engineering text. Volume 1, Foundations, Frameworks, and Quantitative Methodologies. Forward Senior Vice President of Engineering, Global Infrastructure Firm, or former Director of a National Safety Board. The foreword provides an external, high-level validation of the book's importance, speaking to its practical necessity from an industry perspective. Content: we live in an age of unprecedented complexity and interconnection. The engineering systems we design, from global supply chains and energy grids to autonomous vehicles and satellite constellations, are marvels of human achievement. Yet, with this complexity comes profound vulnerability. A minor component failure in one subsystem can cascade into a catastrophic system-wide event, with staggering human, financial, and environmental consequences. We have seen this play out in headlines detailing industrial accidents, cyber-physical system breaches, and infrastructure failures for decades. We have managed risk in silos: safety engineering, financial risk, project management, and cybersecurity often operated as separate domains with their own languages and tools. This fragmented approach is no longer tenable. The imperative for today's engineering leaders is to adopt a holistic, integrated view of risk and decision-making. This volume, Foundations, Frameworks, and Quantitative Methodologies, arrives at a critical time. It provides the essential bedrock upon which a new discipline of integrated risk management is being built. The editors and contributors have masterfully synthesized a body of knowledge that is both academically rigorous and intensely practical. They move beyond theory to provide the frameworks and, most importantly, the quantitative methodologies needed to move from intuitive guesswork to evidence-based decision-making under uncertainty. This book will become a mandatory reference for my engineering teams. It challenges us to think differently, to quantify what we once only qualified, and to make decisions that are robust, resilient, and defensible. It is a vital step towards engineering a future that is not only innovative but also safe, secure, and sustainable. I commend the editors for their vision and urge every engineer, manager, and executive who designs, builds, or operates complex systems to engage deeply with the foundational material presented in this volume. Preface by the editors. The preface is written by the editors to the reader, explaining the book's origin, scope, structure, and intended audience. Content: this book was born from a shared frustration and a common observation. The frustration emerged from witnessing brilliant engineering projects derailed by unforeseen risks that fell between the cracks of traditional management disciplines. The observation was that a new, unified approach was emerging in the most advanced corners of industry and academia, yet no single text served as its cornerstone. Our primary objective with Volume 1, Foundations, Frameworks, and Quantitative Methodologies, is to assemble and organize the core principles and tools required for integrated risk and decision management, IRDM. This volume is not a survey of risks, it is a treatise on how to think about and manage risk cohesively. We focus on the foundational concepts that are universal across engineering domains, the frameworks that provide structure, and the quantitative methods that provide clarity, scope, and audience. This volume is designed for a broad audience: students of systems engineering, industrial engineering, civil engineering, and related fields will find it a textbook that bridges classical theory with modern practice. Practicing engineers and project managers will use it as a handbook for developing risk models, constructing decision frameworks, and justifying investments in risk mitigation. Senior leaders and executives will benefit from the frameworks that translate technical risk into business and strategic implications. Structure of this volume: the book is organized into 3 logical parts. 1 Part I, Foundations, establishes the language of risk and decision theory. It covers core concepts like uncertainty, probability, utility, and the psychology of decision-making. 2 Part II, Frameworks, provides the scaffolding for application. It explores structured processes like ISO 31000, systems theoretic, process analysis, STPA, and bow-tie analysis, teaching you how to structure a risk analysis. 3 Part III, Quantitative Methodologies, is the toolbox. It delves into the math and algorithms, from Monte Carlo simulation and Bayesian networks to fault tree analysis and multi-criteria decision analysis, MCDA, providing the means to populate your frameworks with data and derive actionable insights. Acknowledgements: we are deeply indebted to the countless scholars and practitioners whose work forms the basis of this field. Our contributing authors, experts in their respective domains, have generously shared their knowledge and insights. We also thank our reviewers for their rigorous feedback and our families for their patience and support throughout this demanding project. Our hope is that this volume will serve as a guide and an inspiration, empowering a new generation of engineers to build a world that is inherently safer and more resilient. Introduction: the imperative of integrated risk and decision management in engineering. The introduction sets the stage for the entire book, arguing why this topic is critically important now. Content 1: the age of complexity and interdependence. The engineering landscape has fundamentally shifted. Where we once built discrete, mechanical systems, we now engineer complex socio-technical ecosystems. A modern automobile is a network of computers on wheels. A smart city integrates infrastructure, IoT sensors, and human behavior. A power grid balances renewable generation with digital market mechanisms. This interdependence creates new emergent behaviors that are often impossible to predict from the components alone. In this environment, traditional, reductionist risk management methods are insufficient. To the high cost of fragmented risk management. History is littered with examples of catastrophic failures that resulted not from a single unknown risk, but from a failure to understand how risks interact across domains. A financial decision, cost-cutting, can create a technical risk. Poor maintenance, which is compounded by a human factors risk, inadequate training, and exacerbated by a cultural risk. Poor reporting culture. When these domains are managed in isolation by separate departments, the system-level vulnerability remains invisible until it is too late. The losses are measured in lives, billions of dollars, and ecological damage. 3. Defining integrated risk and decision management, IRDM. Integrated risk and decision management, IRDM, is a paradigm that consciously rejects these silos. It is a systematic, holistic process for identifying risks across all domains: technical, operational, financial, strategic, reputational, cybersecurity, understanding the interactions and couplings between these risks, quantifying their potential impact on system-level objectives using a common scale, e.g., monetary value, utility, informing rational, evidence-based decisions on how to mitigate, transfer, or accept risk in alignment with organizational goals. IRDM is not merely a technical function, it is a core leadership and strategic discipline for the path forward, from philosophy to practice. While the philosophy of IRDM is compelling, its practice demands a specific set of skills and tools. Philosophy must be translated into structured frameworks, and frameworks must be powered by rigorous quantitative methodologies. This translation is the central mission of this book. We will argue that effective IRDM rests on a tripod: foundational theory, a deep understanding of probability, statistics, and cognitive biases; structured processes, repeatable frameworks for risk assessment and decision analysis; computational power, the ability to model complex systems, simulate scenarios, and optimize decisions. 5. A guide to the reader. This introduction has outlined the why. The rest of this volume is dedicated to the what and the how. Part I will build your foundational knowledge. Part 2 will provide you with the maps and blueprints, frameworks, to navigate complex risk landscapes. Part 3 will equip you with the precise instruments, methodologies, to take measurements and chart your course. The journey toward integrated risk management is challenging but essential. It requires a shift in mindset and a commitment to quantitative rigor. We invite you to begin that journey here, with the foundations laid out in the following chapters: the systems you design, the projects you manage, and the organizations you lead will be more resilient, robust, and successful for it. Part I, Foundational Concepts, Chapter 1, following the established tone and structure. Part I, Foundational Concepts. Chapter 1, The Nature of Risk in Engineering Systems. Chapter Overview. This chapter establishes the fundamental language and concepts that form the bedrock of integrated risk management. Before one can manage risk, one must understand its essence. This chapter moves beyond colloquial uses of the term risk to provide precise, actionable definitions. It deconstructs risk into its constituent parts, introduces a holistic taxonomy, and traces the historical evolution of risk management thought, Setting the stage for the quantitative frameworks to follow. 11 Definitions: hazard, risk, uncertainty, and safety. This section clarifies the often misused terminology that is central to the discipline. Hazard, an inherent property or condition with the potential to cause harm, damage, or loss. A hazard is a source of danger, not the manifestation of it. Engineering examples: high voltage in a circuit, a toxic chemical in a process pipeline, the kinetic energy of a moving vehicle, a sharp edge on a component, a latent software bug. Risk, the effect of uncertainty on objectives. ISO 31000. More specifically, it is a function of two components: 1. The likelihood, probability or frequency, of a specific event or scenario occurring, and 2. The severity, magnitude, of its consequences. Mathematically, often expressed as risk equals F, likelihood, consequence. This is not simply multiplication but a functional relationship that can be complex. Key point: risk exists only when a hazard intersects with exposure and a pathway to cause harm. A high voltage line in a deserted area is a hazard. It becomes a risk when a maintenance crew is scheduled to work near it. Uncertainty, a state of deficiency of information related to, understanding of, or knowledge of an event, its consequence, or likelihood. Uncertainty is the fundamental substrate from which risk emerges. Aleatory uncertainty, irreducible uncertainty due to the inherent randomness of a phenomenon, e.g., time to failure of a specific component, wind speed at a site next year. Epistemic uncertainty, reducible uncertainty due to a lack of knowledge or data, e.g., imprecision in a model, limited test data. A primary goal of risk analysis is to reduce epistemic uncertainty through study and measurement. Safety, the state of being protected from or not exposed to danger or risk, the condition of being free from harm or loss. In engineering terms, safety is not the absolute absence of hazards but the effective management and control of risk to a level that is as low as reasonably practicable, ALARP, or tolerable. 12 Anatomy of an engineering risk: sources, causes, events, impacts. This section deconstructs a risk event into a sequence of elements, providing a structured way to analyze any incident. Sources of risk, the fundamental origins from which risk emanates. These can be internal, e.g., design flaws, human error, or external, e.g., market shifts, earthquakes. Causes, threats or triggers: the specific actions, events, or conditions that initiate a sequence of events. A cause acts upon a hazard. Example: corrosion. A cause weakens a pipeline. A hazard, events, incidents or top events: the specific occurrence or change of a particular set of circumstances. This is the central moment of the risk scenario. Near miss, an event that could have resulted in consequences but did not. Precursor event, an event that signals an increased likelihood of a major event. Top event, the central, undesired event being analyzed, e.g., pipeline rupture. Impacts, consequences: the direct and indirect outcomes of the event. Impacts can cascade and amplify: direct, fire, explosion, environmental spill, system downtime. Indirect, financial loss, regulatory fines, reputational damage, loss of public trust. Barriers and controls, the physical or administrative measures put in place to prevent, control, or mitigate the risk scenario. The failure of these barriers is often a critical part of the cause. Example: a pressure relief valve, barrier, fails to activate, failed barrier, allowing pressure to build beyond the design limit. Cause, leading to a vessel rupture. Top event. 13 Classification of risks: technical, operational, financial, strategic, reputational. A holistic IRDM approach requires looking beyond purely technical failures. This taxonomy ensures a comprehensive risk identification process. Technical risk, risks associated with the design, technology, and physical implementation of a system. Examples: component failure, software errors, performance shortfalls, integration problems, scientific uncertainty. Operational risk, risks arising from the day-to-day execution of processes, including human factors and supply chain issues. Examples: human error, operator fatigue, logistics failure, supplier bankruptcy. Maintenance errors. Financial risk, risks related to the economic viability and financial management of a project or organization. Examples: cost overruns, currency fluctuation, interest rate changes, budget cuts, liquidity risk. Strategic risk, risks that affect or are created by an organization's strategic business decisions. Examples: launching a competing technology, changes in regulatory landscape, major shifts in market demand, geopolitical events. Reputational risk, risks of damage to public perception, brand value, or stakeholder trust. Examples: negative media coverage from a safety incident, social media backlash, loss of customer confidence. The interconnection, a single event often triggers risks across multiple categories. A technical failure, technical, may cause a plant shutdown; operational, leading to lost revenue; financial, prompting a re-evaluation of expansion plans; strategic, and generating negative press. Reputational. 14 The evolution of risk management thought. In engineering, this section provides historical context, showing how practice has evolved towards integration. The reactive era, trial and error, reliance on past experience and failure. The primary method was post-accident investigation and correction, learn from mistakes. The prescriptive era, codes and standards, development of prescriptive safety codes, standards, and regulations based on historical data and conservative design principles focused on ensuring a minimum, well-defined level of safety limits. Innovation. The probabilistic era, quantitative risk analysis, QRA, the introduction of probability theory to quantify likelihood and consequences, pioneered in the nuclear, aerospace, and chemical industries, e.g., fault tree analysis, event tree analysis, moved from "is it safe" to "how safe is it?" The systemic era, socio-technical systems, recognition that human and organizational factors are integral parts of the system, not external influences. Frameworks like STPA, systems theoretic process analysis, and resilience engineering focus on interactions, emergent behavior, and ensuring systems can adapt under stress. The integrated era, IRDM, the current evolution, which seeks to break down silos between risk types, technical, financial, etc., and integrate risk management into the core of organizational strategy and decision-making. It leverages the tools of all previous eras within a holistic, model-based framework. Chapter summary. This chapter has provided the essential vocabulary and conceptual models for understanding risk. We have defined its core components, deconstructed its anatomy, classified its various forms, and traced its intellectual history. This foundational knowledge is a prerequisite for the next step, learning how to structure and execute a systematic risk management process, which is the focus of Chapter 2. Chapter 2, Principles of Engineering Decision-Making, continuing the academic and professional tone of the volume. Chapter 2, Principles of Engineering Decision-Making. Chapter Overview. Engineering is fundamentally a discipline of decision-making under constraints. This chapter transitions from understanding risk to making informed choices in the face of that risk. We explore the theoretical models of how decisions should be made and contrast them with the empirical reality of how they are made by understanding the limitations of pure rationality, the power of structured multi-criteria frameworks, and the pervasive influence of cognitive biases. The engineer is equipped to create more robust, defensible, and effective decision-making processes. 21 Rational choice theory and its limitations. This section establishes the classical, normative model of decision-making against which all real-world processes are compared. Core tenets of rational choice theory. RCT. Goal-oriented actor. The decision-maker has a clear and consistent set of objectives, e.g., maximize utility, minimize cost, complete information, all possible alternatives, their consequences, and the probabilities of those consequences are known or knowable. Unlimited cognitive capacity. The decision-maker can process all available information to identify the optimal choice. Utility maximization. The decision-maker will choose the alternative that yields the highest expected value or utility. Application in engineering. RCT provides the foundation for powerful quantitative tools like expected monetary value, EMV, analysis, EMV equals sigma, probability of outcome _ I, value of outcome _ I, cost-benefit analysis, CBA is systematic approach to estimating the strengths and weaknesses of alternatives. Key limitations in engineering practice: information is never complete, probabilities are often estimates, and long-term consequences are inherently uncertain. Epistemic uncertainty: objectives are rarely singular or simple. Engineers must balance cost, safety, performance, schedule, and environmental impact, which are often in conflict. Cognitive limits: it is impossible for a human or even an organization to identify and evaluate every conceivable alternative. The assumption of rationality ignores the profound influence of human psychology, organizational politics, and culture. 22 Bounded rationality and satisficing in complex projects. This section introduces a more realistic descriptive model of how decisions are actually made within the constraints of the real world. Herbert Simon's concept. Bounded rationality is the idea that the rationality of individuals is limited by 1. The information they have, 2. The cognitive limitations of their minds, 3. The finite amount of time they have to make a decision. Satisficing, a decision-making strategy that entails searching through the available alternatives until an acceptability threshold is met. Instead of maximizing, finding the best possible option, decision-makers satisfice, find an option that is good enough. Engineering example: selecting a standard, proven material for a component, a good enough choice that meets all requirements, rather than spending excessive time and resources searching for a theoretically optimal but novel and risky material. Implications for engineering management: acknowledging bounded rationality justifies the need for structured decision-making processes, checklists, and expert consultation to expand the bounds of what is rational for an individual. It highlights the importance of defining clear aspiration levels or minimum criteria that a solution must meet, making the satisficing process more transparent and defensible. 23 Multi-criteria decision-making, MCDM, fundamentals. This section provides the primary toolkit for moving beyond single objective, e.g., just cost, decision-making, which is essential for integrated risk management. The need for MCDM: engineering decisions almost always involve trading off between multiple, competing objectives, e.g., safety vs cost, weight vs strength, performance vs time to market. Core process of MCDM: 1. Define the problem and identify alternatives, list the viable options. 2. Select relevant criteria, establish the dimensions of value, e.g., cost, reliability, environmental impact, technical maturity, these must be measurable. 3. Weight the criteria, determine the relative importance of each criterion, e.g., is safety twice as important as cost? 4. Score alternatives, evaluate how well each alternative performs on each criterion. 5. Synthesize scores and weights, use a formal method to aggregate the data and rank the alternatives. Common MCDM methods: weighted sum model, WSM. The simplest method, scores are multiplied by weights and summed. Highly transparent but requires a linear utility function. Analytic hierarchy process, AHP. A more sophisticated method that uses pairwise comparisons of criteria and alternatives to derive weights and scores, and can also check for consistency in judgments. Utility theory assigns a utility value to outcomes that reflects the decision-maker's risk preference, e.g., risk-averse, risk-seeking. 24 The role of heuristics and biases in engineering judgment. This section explores the psychological underpinnings of judgment, explaining why expert intuition can sometimes lead to systematic errors. Heuristics, mental shortcuts or rules of thumb that simplify complex judgment tasks. They are often efficient and effective, but can lead to predictable errors. Availability heuristic, estimating the likelihood of an event based on how easily examples come to mind, e.g., overestimating the risk of a recent, vivid failure. Anchoring and adjustment, relying too heavily on an initial piece of information, the anchor, when making decisions, e.g., an initial cost estimate unduly influencing all subsequent estimates. Representativeness heuristic, judging the probability of an event by how similar it is to a known process, while ignoring base rates, e.g., assuming a new, complex project will be similar to a past, simpler one. Cognitive biases, systematic patterns of deviation from norm or rationality in judgment. Confirmation bias, the tendency to search for, interpret, and recall information in a way that confirms one's pre-existing beliefs. Overconfidence bias, an unwarranted faith in one's own intuitive reasoning, judgments, and cognitive abilities. Planning fallacy, the tendency to underestimate the time, costs, and risks of future actions and to overestimate the benefits. Mitigating biases in engineering practice, awareness and training, recognizing that these biases exist is the first step. Process and procedures, implementing standardized review processes, e.g., design reviews, peer reviews, pre-mortems, that challenge assumptions. Quantitative support, using the MCDM and risk quantification tools from previous sections to provide an objective counterweight to intuition. Chapter summary: effective engineering decision-making requires a blend of art and science. It acknowledges the ideal of rational choice while operating within the realistic bounds of human cognition and information scarcity. By employing structured frameworks like MCDM and maintaining a vigilant awareness of inherent heuristics and biases, engineers can transform decision-making from an opaque art of intuition into a transparent, defensible, and rigorous process. This sets the stage for the specific frameworks and methodologies covered in parts 2 and 3 of this volume. Chapter 3, the regulatory and ethical landscape, maintaining the rigorous, academic, and practical tone of the volume. Chapter 3, the regulatory and ethical landscape. Chapter overview: engineering decisions are not made in a vacuum, they are bounded by a critical framework of professional ethics and legal obligations. This chapter explores the non-technical constraints that fundamentally shape risk management. Understanding this landscape is not merely about avoiding litigation, it is about fulfilling the engineer's fundamental duty to society. We will examine the ethical codes that guide professional conduct, the legal doctrines that enforce accountability, the philosophical underpinnings of safety standards, and the challenges of applying caution in the face of innovation. 31 Engineering Codes of Ethics and Risk. This section establishes the moral imperative for integrated risk management, as defined by the profession itself. The foundation, hold paramount the safety, health, and welfare of the public. This principle, common to virtually every engineering code of ethics worldwide, e.g., from the NSPE, ASCE, IEEE, is the primary ethical driver for risk management. It positions risk assessment and mitigation not as a business function, but as a core professional obligation. Key ethical duties related to risk: duty of disclosure, the obligation to inform clients, employers, and the public of potential risks associated with a project or product. This includes whistleblowing in cases where there is an imminent threat to public welfare. Informed consent, ensuring that all affected parties understand the risks they are being exposed to, especially in public infrastructure projects or new technologies. Competence, performing services only in areas of one's competence. This implies that risk assessments must be conducted by, or under the supervision of, qualified professionals. Sustainability, a modern addition to many codes, requiring engineers to consider the long-term environmental and social risks of their projects, promoting sustainable development. Case studies, analysis of historical failures, e.g., Challenger Space Shuttle, Ford Pinto, through the lens of ethical code violations, highlighting the consequences of prioritizing schedule or cost over safety. 32 Legal frameworks, liability, negligence, and duty of care. This section translates ethical duties into legal consequences, outlining the system of accountability that governs engineering practice. Duty of care, a legal obligation imposed on an engineer requiring adherence to a standard of reasonable care while performing any acts that could foreseeably harm others. This duty is owed to clients, employers, and any third party who could be reasonably affected by the work. Negligence, the breach of a duty of care in engineering. This is often established by showing that the professional, 1, owed a duty of care to the plaintiff, 2, breached that duty by failing to meet the standard of care, 3, the breach caused the plaintiff's injury or loss, 4, there were damages. Standard of care, the degree of prudence and caution required of an engineer who is under a duty of care. It is typically defined as the level of care and skill that a reasonably competent engineer practicing in the same field would provide under similar circumstances. This is why adherence to established codes and standards is a primary defense against negligence claims. Strict liability vs. negligence, discussion of doctrines that apply primarily to product design, where a manufacturer may be held liable for a defective product even without proof of negligence, e.g., in cases of flawed design or inadequate warnings. 33 Compliance vs Performance-Based Standards. This section examines the two primary philosophical approaches to regulation, which shape how risk is managed in different industries: prescriptive, compliance-based. Standards. Definition: standards that specify how to achieve safety, the exact materials, designs, techniques, and processes that must be used. Examples: many building codes, e.g., specific seismic bracing details. Older machinery safety standards. Advantages: clear, easy to enforce and inspect, provide certainty. Disadvantages: can stifle innovation, may not be suitable for novel technologies or complex systems, can create a check-the-box mentality where compliance is mistaken for safety. Performance-based standards. Definition: standards that specify what outcome must be achieved, e.g., must contain a spill, must ensure radiation exposure is below X limit, but do not prescribe how to achieve it. Examples: modern process safety management standards, e.g., OSHA PSM 29 CFR 191-0119, functional safety standards, IEC 61508. Advantages: promotes innovation and flexibility, allows engineers to find the most efficient solution, adaptable to new technologies. Disadvantages: more difficult to enforce, requires greater expertise and judgment from both the engineer and the regulator, places a higher burden of proof on the designer to demonstrate that the standard is met. The convergence. The trend in modern regulation is toward a hybrid model, using performance-based goals underpinned by prescriptive means of compliance as accepted methods. 34 The precautionary principle in engineering innovation. This section tackles the complex challenge of managing risk when dealing with profound uncertainties, such as in emerging technologies like nanotechnology, AI, or genetic engineering. Definition: a strategy for approaching potential risks when scientific understanding is incomplete and the possibility of severe or irreversible harm exists. In essence, where there are threats of serious or irreversible damage, lack of full scientific certainty shall not be used as a reason for postponing cost-effective measures to prevent environmental degradation. Rio Declaration, 1992. Interpretations and applications. Strong precaution shifts the burden of proof. Innovators must demonstrate that a new technology is safe before it can be deployed, e.g., the EU's approach to GMOs. Weak precaution calls for a careful, deliberative process of risk research and monitoring alongside development and adaptive management, e.g., learning and adjusting regulations as new information emerges. Criticisms and challenges. Paralysis by analysis can be used to stifle innovation and progress. Indefinitely. Ambiguity lacks a clear, operational definition of what level of risk triggers the principle. Ignoring risk of inaction, fails to weigh the risks of not adopting a new technology, e.g., the risks of not developing geoengineering solutions to climate change. Engineering a precautionary approach, how engineers can operationalize the principle through safe life and fail-safe design, designing systems with inherent margins of safety. Phased rollouts and pilots, limiting the scale of initial deployment. Monitoring and adaptive management, building systems to learn from performance and adjust accordingly. Redundancy and resilience, designing systems to withstand or gracefully degrade from unanticipated failures. Chapter summary. The regulatory and ethical landscape provides the rules of the game for engineering risk management. It moves the discipline from a technical exercise to a socio-technical one, where quantitative risk calculations must be interpreted within a framework of moral duty and legal accountability. The most sophisticated risk model is worthless if it ignores the engineer's ethical obligation to the public or fails to meet the legal standard of care. Understanding the tension between prescriptive compliance and performance-based goals, and navigating the uncertainties of innovation with a precautionary yet pragmatic approach, are hallmarks of the modern engineering leader. This chapter provides the essential foundation for operating effectively within this critical landscape. Chapter 4, Qualitative Risk Analysis Techniques, adhering to the structure and academic professional tone established in the previous chapters. Part 2, Risk Identification and Assessment Methodologies. Chapter 4, Qualitative Risk Analysis Techniques Chapter Overview. Before risks can be quantified, they must be identified and understood. Qualitative analysis forms the crucial first pass in any risk management process, providing a structured approach to uncover, categorize, and prioritize risks. This chapter introduces the foundational techniques used to systematically brainstorm and filter risks. These methods are efficient, require minimal data, and are essential for building the comprehensive risk register that will later be analyzed with more quantitative tools. The output of this chapter is a prioritized list of risks, providing a clear direction for further, more resource-intensive analysis. 41 Brainstorming, Delphi Method, and Expert Elicitation. This section covers techniques for generating a comprehensive list of potential risks by leveraging collective intelligence. Brainstorming, Purpose, a group creativity technique designed to generate a large number of ideas spontaneously and without criticism. Process, a facilitated session with a diverse group of stakeholders, engineers, operators, managers. Rules include: defer judgment, encourage wild ideas, build on the ideas of others, and go for quantity. Strengths, fast, collaborative, can uncover unexpected risks through cross-disciplinary discussion. Weaknesses, susceptible to groupthink, dominance by senior personnel, and the anchoring effect. Delphi Method, Purpose, a structured communication technique designed to achieve a consensus of opinion from a panel of independent experts without physical meeting. Process, 1. Anonymously solicit ideas and estimates from experts via questionnaires. 2. Summarize and share the anonymous results with the panel. 3. Experts review the summary and are given a chance to revise their earlier answers. 4. The process iterates until a consensus is reached. Strengths, eliminates groupthink and bias from dominant individuals, leverages geographically dispersed expertise. Weaknesses, time-consuming, requires significant facilitation effort, can lack the creative synergy of live interaction. Expert elicitation, Purpose, the formal process of obtaining subjective judgments from experts on topics where objective data is scarce or non-existent. Process, a structured interview with a single expert or a small panel, often using techniques to calibrate the expert's confidence and mitigate overconfidence bias, e.g., asking for confidence intervals, using seed questions from their domain of expertise. Application, critical for assigning initial probability and impact ratings for novel or complex risks in the absence of historical data. 42 Checklists and prompt lists. This section discusses tools that leverage historical knowledge and past experience to ensure common risks are not overlooked. Checklists, Purpose, a standardized list of known risks or failure modes based on lessons learned from past projects, industry experience, or regulatory requirements. Usage, the team goes through the list item by item to determine if each risk is applicable to the current project or system. Example, a project management checklist might include items like supplier has single point of failure, key person dependency exists, or regulatory approval timeline is aggressive. Strengths, simple, quick, and excellent for ensuring known unknowns are not forgotten. Embodies organizational learning. Weaknesses, can induce a false sense of security. If it's not on the list, it doesn't exist. Not effective for identifying novel or emergent risks. Prompt lists, Purpose, a more flexible tool than a checklist, designed to stimulate thinking rather than provide a yes/no answer. They are often organized by risk category. Usage, provides categories, e.g., technical, operational, external, organizational, and example questions or prompts under each example. Under technical risk, what assumptions have we made about material performance? How stable are the interfaces between subsystems? Strengths, more generative than a checklist, helps teams think more broadly without constraining them to a fixed list. Weaknesses, less comprehensive than a detailed checklist for common risks. 43 Preliminary hazard analysis, FOT. This section introduces a foundational, systematic technique for identifying hazards and their potential causes and effects early in a system's life cycle. Purpose, a high-level, inductive risk analysis method used primarily in the conceptual and design phases to identify potential hazards, their causes, and their consequences. It is often the first structured safety review of a system process, typically conducted by a small team using a worksheet to systematically consider system components, energy sources, and interactions. Worksheet columns typically include 1. Hazard, the identified hazardous element or condition, e.g., high pressure, rotating machinery, toxic substance. 2. Potential causes, events that could realize the hazard, e.g., corrosion, human error, software fault. 3. Potential consequences, the possible outcomes if the hazard is realized, e.g., rupture, injury, environmental release. 4. Severity rating, a qualitative rating of the worst plausible consequence, e.g., catastrophic, critical, marginal, negligible. 5. Recommended actions, initial ideas for mitigation, e.g., add pressure relief valve, implement interlocks. Output, a FAR report that provides an initial risk assessment and a list of safety recommendations to be incorporated into the design. It is a primary input for more detailed analyses like HAZOP or FMEA-44 risk matrix and risk register development. This section covers the tools used to consolidate, prioritize, and communicate the results of qualitative analysis. Risk matrix, risk assessment matrix. Purpose, a graphical tool used to define the level of risk by considering the category of probability or likelihood against the category of consequence. Severity. Structure, y-axis, likelihood, e.g., frequent, probable, occasional, remote, improbable. X-axis, severity, e.g., catastrophic, critical, marginal, negligible. Cells, the intersection of likelihood and severity defines a risk level, e.g., high, medium, low, often color-coded, red, yellow, green. Usage, provides a consistent, visual method for comparing and prioritizing diverse risks. A high risk, high likelihood, high severity, requires immediate action, while a low risk may be accepted or monitored. Risk register. Purpose, the central repository for all identified risks, their assessments, and planned responses. It is the living document of the risk management process. Key fields in a risk register: 1. Risk ID, a unique identifier. 2. Risk description, a clear statement of the risk, cause, event, effect. 3. Causes and triggers, what could cause the risk to occur. 4. Impacts, the consequences on objectives. 5. Likelihood and severity ratings, e.g., from the risk matrix. 6. Risk level, the resulting priority, e.g., high/medium/low. 7. Risk owner, the person responsible for managing the risk. 8. Mitigation action/response plan, the steps to avoid, transfer, mitigate, or accept the risk. 9. Status, e.g., open, in progress, closed. Role in IRDM, the risk register is the tangible output that integrates risks from all domains, technical, operational, etc., into a single, manageable list, enabling informed decision-making at all levels of the organization. Chapter summary: qualitative risk analysis is not a simplistic exercise, it is a structured and essential discipline for uncovering and prioritizing threats. The techniques in this chapter, from leveraging expert judgment to applying systematic frameworks like FA, provide the necessary foundation for all subsequent quantitative analysis. The risk matrix offers a mechanism for consistent prioritization, while the risk register serves as the master document for tracking and managing risk throughout the project life cycle. This qualitative groundwork ensures that quantitative efforts are focused efficiently on the areas of highest concern. Chapter 5, Failure-Oriented Analytical Techniques, continuing the rigorous and practical approach of the volume. Chapter 5, Failure-Oriented Analytical Techniques. Chapter overview: qualitative techniques identify what can go wrong. Failure-oriented analytical techniques provide the structure to understand how and why it can go wrong, and what the consequences will be. This chapter delves into 4 powerful, inductive, and deductive methodologies that form the backbone of detailed technical risk assessment. These techniques move beyond lists to create logical models of failure, enabling a deeper understanding of system vulnerabilities, the quantification of probabilities, and the identification of critical components. Mastery of these methods is essential for any engineer tasked with demonstrating the safety and reliability of a complex system. 51 Failure mode and effects analysis, FMEA/FMEA. This section covers a bottom-up, inductive technique focused on component-level failures and their system-level effects purpose, a systematic, bottom-up method for identifying potential failure modes of components, determining their effects on the system, and prioritizing actions to mitigate the most critical failures. FMEA, failure mode, effects, and criticality analysis, is an extension that adds a criticality analysis to rank the failure modes based on their severity and probability of occurrence process, typically performed by a cross-functional team using a standardized worksheet. 1. Identify components/functions, decompose the system into its constituent parts or functions. 2. Identify failure modes, for each component, list all the ways it can fail, e.g., open circuit, short circuit, leak, stuck open, stuck closed. 3. Determine effects. 4. Each failure mode, describe the local, system level, and ultimate end effects. 4. Identify causes, determine the root cause, of each failure mode. 5. Identify existing controls, list current design provisions or procedures that detect or mitigate the failure. 6. Assign risk priority numbers, RPN severity, rating of the seriousness of the effect, 1 to 10, occurrence, O rating of the likelihood of the failure occurring, 1 to 10, detection, D rating of the ability of current controls to detect the failure before it occurs or before it reaches the customer, 1 to 10, RPN equals S times O times D. Failures with high RPNs are prioritized for corrective action applications, widely used in manufacturing, automotive, aerospace, and healthcare industries for design and process review. Strengths and weaknesses. Strengths, highly systematic, excellent for detailed component-level analysis, promotes proactive thinking. Weaknesses, can be tedious for large systems, does not easily capture human error or external events, and does not model combinations of failures, addressed by FTA-52. Fault tree analysis, FTA. This section introduces a top-down, deductive technique used to analyze the causes of a specific, undesired top event. Purpose, a deductive, graphical technique used to determine the various combinations of hardware and software failures, human errors, and external events that can lead to a specified undesirable system event. The top event, process and syntax. 1. Define the top event, the specific, undesired system-level event to be analyzed, e.g., reactor core meltdown, loss of braking. 2. Construct the tree downward, using standard logic symbols, and gates, or gates, identify the immediate and necessary causes of the event. 3. Develop to sufficient depth, continue decomposing causes until reaching basic events, component failures, human errors, that require no further development. 4. Analyze the tree, identify minimal cut sets, the smallest combination of basic events that, if they all occur, will cause the top event. This reveals the system's most vulnerable pathways. Quantification, if probabilities are assigned to basic events, the probability of the top event can be calculated through the logic gates, or gates add probabilities, and gates multiply them, with approximations for rare events. Applications, crucial for safety engineering in nuclear power, aerospace, and chemical processing industries. Excellent for analyzing complex failure combinations. Strengths and weaknesses. Strengths, excellent for modeling complex combinations of failures, provides clear visual representation of failure logic, enables quantitative probability calculation. Weaknesses, a single tree is built for one top event only. Analyzing all risks requires multiple trees, can become extremely complex for large systems. 53. Event tree analysis, EDA. This section covers an inductive technique that begins with an initiating event and explores the range of possible outcomes based on the success or failure of safety systems. Purpose, an inductive, forward-looking technique that begins with an initiating event and models the various possible sequences of events that follow, based on the success or failure of installed safety barriers or mitigating functions. Process, 1. Identify initiating event, the initial failure or event that starts the accident sequence, e.g., loss of coolant, gas leak. 2. Identify safety barriers, list the systems, functions, or human actions that are designed to intervene and mitigate the event, e.g., emergency core cooling system, gas detector alarm, operator intervention. 3. Construct the tree. For each barrier, the tree branches into two paths: success, barrier works, and failure, barrier fails. 4. Define outcomes. The end of each branch represents a distinct outcome scenario with its own consequences, e.g., minor leak contained, explosion. Quantification. By assigning probabilities of success/failure to each barrier, the probability of each outcome scenario can be calculated. Applications, often used in conjunction with FTA. The top event of a fault tree can become the initiating event of an event tree, common in probabilistic risk assessment, PRA, for nuclear and process plants. Strengths and weaknesses. Strengths, excellent for modeling the timeline of an accident and the role of safety systems, provides a clear view of the spectrum of potential consequences. Weaknesses, only follows from one initiating event at a time. Requires a well-defined understanding of the system's response. 54 Bowtie analysis. This section presents a powerful, intuitive technique that synthesizes the deductive logic of FTA and the inductive logic of EDA into a single, compelling visual model. Purpose, a graphical technique that provides a consolidated view of the entire risk scenario, from causes to consequences, and maps the controls, barriers, in place to manage it. The Bowtie structure. Central knot, the top event or hazardous event, e.g., tanker grounding, left-hand side. Fault tree logic illustrates the potential causes that could lead to the top event. These are called threats. Right-hand side. Event tree logic illustrates the potential consequences that could result from the top event. Barriers, controls. The key elements of the Bowtie. They are depicted as vertical bars between threats and the top event. Preventive barriers, the top event and consequences. Mitigative barriers. Process. 1. Define the hazardous event, not. 2. Identify threats, causes, and consequences. 3. Identify all existing preventive and mitigative barriers. 4. Analyze the effectiveness of each barrier, e.g., strength, reliability, independence. 5. Identify escalation factors, conditions that can weaken a barrier and the controls to manage those. Degradation controls. Applications, extremely effective for risk communication to management and operators, as it tells the complete story of a risk in one diagram. Widely used in high-hazard industries like oil and gas, aviation, and mining. Strengths and weaknesses. Strengths, superior visual communication tool, integrates proactive and reactive risk management, facilitates a discussion on barrier effectiveness. Weaknesses, can become visually cluttered for very complex scenarios, less suited for detailed quantitative analysis than FTA/EDA. Chapter summary. The techniques in this chapter, FMEA, FTA, EDA, and Bowtie, are not mutually exclusive, they are complementary tools in the risk analyst's toolkit. FMEA provides granular, component-level insight. FTA offers deep root cause analysis for specific events. EDA forecasts potential consequences. Bowtie synthesizes everything for holistic risk understanding and communication. Selecting the right technique, or combination of techniques, depends on the system's complexity, the analysis objectives, and the available data. Together, they form a robust methodology for deconstructing failure and building a compelling case for safety. Chapter 6, Quantitative Risk Assessment, QRA, designed to follow the structure and depth of the previous chapters. Chapter 6, Quantitative Risk Assessment, QRA, Chapter Overview, Qualitative and Failure-Oriented Techniques. Prioritize and structure risks. Quantitative Risk Assessment, QRA, assigns them numerical values. This chapter equips the engineer with the mathematical and computational tools to move from statements like high risk to predictions like a 23% probability of exceeding the budget by $5 million. QRA transforms risk management from a descriptive exercise into a predictive and rigorously analytical discipline. It enables cost-benefit analysis of mitigation strategies, supports data-driven decision-making, and is often required to demonstrate safety and financial viability for large, complex projects. This chapter covers the essential probability theory, statistical methods for handling real-world data, and powerful simulation and modeling techniques that form the core of Modern QRA-61 Fundamentals of Probability Theory for Engineers. This section reviews and frames probability concepts not as abstract mathematics, but as the essential language of uncertainty for engineering applications. Probability as a measure of uncertainty, framing probability in the context of epistemic, knowledge-based, and aleatory, inherent randomness, uncertainty. Core concepts for QRA, probability axioms, foundation for all quantitative analysis. Conditional probability, P.A.B. The probability of an event given that another event has occurred. Fundamental for understanding dependent failures and updating beliefs. Bayes' theorem, introduced as a mechanism for updating prior beliefs with new evidence. P.A.B. equals P.B.A. P.A/P.B. This sets the stage for Bayesian networks later in the chapter. Probability distributions, not just as functions, but as models for engineering variables. Discrete distributions, binomial, modeling pass/fail trials, Poisson, modeling arrival rates of failure events, continuous distributions, normal, modeling measurement errors, log normal, modeling failure times, costs, exponential, modeling time between independent events, weighable, versatile for reliability data, application focus, how to select an appropriate distribution based on the nature of the data, e.g., why is the log normal distribution often a better fit for project cost than the normal distribution? 62 Statistical methods for failure data analysis. This section bridges the gap between theoretical distributions and the messy reality of sparse, censored, and incomplete engineering data. Data challenges in engineering, dealing with small sample sizes, censored data, components that haven't failed yet, and conflicting data sources. Parameter estimation, methods for fitting distributions to data. Method of moments, simple but often less accurate. Maximum likelihood estimation, MLE, the preferred method for most reliability applications, as it provides robust, unbiased estimates, especially with censored data. Reliability engineering metrics, deriving actionable metrics from failure data and distributions. Reliability function, R.T. the probability that a component will perform its intended function for a specified time period. Failure rate, hazard function, H.T. the instantaneous rate of failure at a given time. Discussing the bathtub curve concept. Mean time to failure, MTTF/mean time between failures, MTBF. Their calculation and common misapplications. Introduction to survival analysis, techniques for analyzing time to event data, crucial for maintenance and replacement planning. 63 Monte Carlo simulation for cost and schedule risk. This section introduces one of the most powerful and widely used tools for quantifying uncertainty in project outcomes: the limitation of deterministic estimates, the fallacy of the single point estimate, e.g., the project will cost $10M, and the point and press mentality of traditional scheduling. The Monte Carlo method, concept, a computational technique that uses random sampling from input distributions to simulate a process thousands of times and compute a distribution of possible outcomes. Process 1. Model building, create a parametric cost or schedule model, e.g., in Excel or specialized software. 2. Define input uncertainties, assign probability distributions to all uncertain input variables, e.g., cost of materials. Log normal, $50,000, $5,000, task duration triangular, 5D, 8D, 14D, 3. Sampling, the software runs the model thousands of times, each time drawing a random value from each input distribution for output analysis. The results are aggregated into a probability distribution for the total cost or project duration. Interpreting results, S-curve, cumulative distribution function used to answer probabilistic questions. What is the probability, confidence, that the project will cost less than $11 million? Or what is the cost for which we have an 80% confidence level? Tornado charts, identify which input variables contribute the most to the output uncertainty, guiding where to focus risk mitigation efforts. Value, moves project forecasting from the cost is $10 million to there is a 70% confidence the cost will be between $92 million and $115M, Enabling proactive contingency planning. 64 Bayesian networks for dynamic risk assessment. This section presents an advanced, flexible methodology that overcomes many limitations of traditional techniques like FTA and EDA. Beyond static techniques, limitations of FTA/EDA, they are often static, assume independent events, and struggle with incorporating new evidence. What is a Bayesian network, BN? A graphical model that represents a set of variables and their probabilistic dependencies via a directed acyclic graph. DAG nodes represent random variables, e.g., sensor fault, operator response, leak size. Arcs represent causal or influential relationships between variables. Conditional probability tables, CPTs, quantify the strength of the relationships for each node. Advantages for engineering risk assessment, handling dependence, explicitly models dependencies between events. Forward, predictive, and backward, diagnostic, analysis, can predict the probability of an outcome and diagnose the most likely cause given an observed effect, e.g., given an explosion, what was the most probable initiating event? Incorporating evidence, the network can be updated in real time as new information is available, e.g., given that the alarm did not sound, how does the probability of a leak change? This makes BNS powerful for dynamic online risk monitoring systems. Modeling common causes, elegantly handles common cause failures that are difficult to model in fault trees. Application example, building a simple BN for a pressure tank system, demonstrating how to model causes, barriers, and consequences, and then updating the model with simulated sensor readings. Chapter summary. Quantitative risk assessment is the engine that powers evidence-based decision-making in engineering. This chapter has provided a roadmap from the fundamental language of probability, through the practicalities of analyzing imperfect failure data, to the application of powerful computational methods like Monte Carlo simulation and Bayesian networks. By translating uncertainties into quantitative metrics, QRA allows engineers to speak the language of management and finance, justifying investments in safety and reliability with concrete probabilistic evidence. It is the critical link between identifying risk and making informed, defensible decisions to manage it. Chapter 7, Systemic and Emerging Risk Approaches, concluding Part 2 of the volume with a forward-looking perspective on modern risk paradigms. Chapter 7, Systemic and Emerging Risk Approaches. Chapter Overview. Traditional risk assessment techniques, while powerful, often struggle with the complexities of modern socio-technical systems. They can be overly focused on component failures and miss the risks that emerge from complex interactions, adaptive behaviors, and unprecedented events. This chapter explores a new frontier of risk methodologies designed to address these challenges. We move from a focus on failure to a focus on control and adaptation, and from protecting against known threats to building systems that can withstand and learn from the unknown. This chapter equips the engineer to address the most daunting risk landscapes of the 21st century, from software-intensive systems to existential threats. 71. System Theoretic Process Analysis, STPA. This section introduces a powerful, modern technique born from systems theory that focuses on ensuring functional safety by enforcing constraints on system behavior beyond component failure. The limitations of traditional methods. STPA is founded on the premise that accidents are not just caused by component failures but more often by unsafe interactions of components that are functioning correctly. This is a fundamental shift from a reliability-centric to a safety-centric view. Foundations in systems theory. Accidents as a result of inadequate control. STPA treats safety as a control problem. Accidents occur when flawed or inadequate control actions, or a lack of control, lead to a violation of system safety constraints. The hierarchical control structure models the entire socio-technical system, including software, hardware, human controllers, and management, showing the flow of information and control loops. The STPA process. 1. Define purpose and identify system-level hazards. 2. Model the control structure, diagram the controllers, actuators, sensors, and controlled processes, along with their interactions. 3. Identify unsafe control actions, UCAs for every control action, systematically identify how it could be provided in an unsafe way, not provided, provided too early, too late, or out of sequence, stopped too soon or applied too long, provided in the wrong context or with the wrong magnitude. For identify loss scenarios, for each UCA. Determine the causal factors and contextual conditions that could lead to it, e.g., flawed process models, feedback delays, component interactions, management decisions, application, particularly dominant in aerospace,